in case of real integrals, so you hand this particular phenomena a to b f of t dt. So this would be minus b to a f of t dt, right? So if you integrate from a to b, whatever you are supposed to get, and then if you integrate from b to a, we'll just get it with a minus sign, right? Yes. So here
Yes,
what
sir.
Yes, sir.
so
Yes, yes, sir.
what we are going to do, we are going to have an analog, complex analog over here. So let us see. I need a complex analog. Okay, so uh, you see here, you can think of, let's say if I have an interval a to b, so you are integrating in this direction, whereas I am going to integrate in the other direction if I have to integrate from b to a. So in case of a path gamma, I have to first tell you about a reverse path, okay, and then we will see how the integration works out. Okay, so first of all, definition: let gamma from closed interval ab to c be a piecewise smooth curve. So I have told you that most often we will work with piecewise smooth curves so that we can directly apply the formula for our integral. That integral of f over gamma is integral a to b f of gamma t gamma prime t dt. So I have a piecewise smooth curve, okay, and then I am going to define a reverse path. Okay, so what do I mean by a reverse path? So let's say I have a gamma over here. So let's say this is gamma of a and this is gamma of b. Okay, so I want to define a new path which, let's say when I start at a, this will start from this particular gamma b, and when I reach the point b, it should end at gamma a. Okay, so in the reverse direction the path should go. So gamma is going in this direction, let's say. So I want to define a new path which at the point a starts takes the value gamma b, and at the point b takes the value gamma a. Okay, so it's the reverse path that I want to define. So define gamma tilde, let's say, from ab to c. Okay, so by the following way. So how can I
A
define
plus
that? Yeah, tell
a
me.
plus b minus t.
Yeah, very good. So not, yeah, exactly. So gamma of a plus b minus t. Very good. So this is what I am going to take. So gamma of a plus b minus t. So this path is going to be the reverse path. Okay, so this path is called the reverse of the reverse of gamma. So essentially, my means trace of this path, these two paths are the same set, except that this gamma. So this point gamma b is now gamma tilde of a, and this point gamma a is now gamma tilde of b. So I am traveling along the same path, exactly the same set of points, but in the reverse direction. Okay, so that's why this is called reverse of gamma, and the statement, or the, as I said, the complex analog that we are going to have over here is just going to be integral over gamma of f is or gamma tilde, let me write, is minus of integral of f over gamma. Okay, so it's just going to change, you are just going to have a minus sign in front of you, that's all, no other changes. Okay, so let's see the proof quickly. So you will see that there will be absolutely no difference at all. So like the proof will be very easy. So gamma tilde f, this is what, this is by definition a to b f of gamma tilde t gamma tilde prime t dt. So that's our definition. Now let us replace what is gamma tilde. So a to b f of gamma of b minus, sorry, b plus a minus t, or a plus b minus t, a plus b minus t. And now tell me, how does gamma prime t and gamma t is related, or rather gamma tilde prime t and gamma of b a plus b minus t, how is it related?
Chain rule.
Yeah, so therefore what am I going to get if I take chain rule? This is going to,
minus.
yeah, gamma prime a plus b minus t. Very good. And there should be a minus in front.
-1.
So yeah, so now I get this one, and then here, of course, you see, we have now learned about what you say, this thing about whatever change of variable in the last class. So here, what is my lambda? My lambda is now going from a b to a b, where the function is t going to a plus b minus t. If I take this particular function, so clearly lambda is 1 1, so injective, and c1. Okay, c1 means continuously differentiable. So this is what we have. So therefore here I am having that this guy, so the integral, let me write down. So the integral was f over gamma tilde is minus a to b f of gamma lambda t times gamma prime of lambda t dt. This is what I have, because this one I have said this is lambda prime or lambda t. So this is what I have, and I can write this as a to b f of gamma of lambda t, and then gamma prime of lambda t is nothing but sorry. Yeah, so what I do here, you see, I need to absorb like I want to make I need to absorb this thing. So here I have gamma prime of lambda t, but I don't have lambda prime t. So what is lambda prime t? Lambda prime t is -1. So here this minus I forget, so I write lambda prime t dt. Okay, so this is nothing but a to b f of your gamma composed lambda of t, and then again gamma composed lambda prime of t dt. And this we already know, the change of variable works absolutely fine. So yeah, uh, okay, so here when I take change of variable, we have seen that lambda of a is equal to b and lambda of b is equal to a. So when I take the change of variable, so what we can do is that we can write that this integral becomes just a moment, this integral becomes integral from b to a f of gamma t gamma prime t dt, and that is nothing but minus of f over gamma. Okay, so this is what we get. One has to be a little bit careful what we are doing. So first of all, here I had a minus already from the last step, which was a minus over here because we were taking what is gamma prime. So I got this minus, and then what I said is that or I could have said here itself that my gamma prime, how do I see gamma prime in terms of this gamma composed lambda? Probably I could have done that. So anyway, so here I have a minus, and you can clearly see that this was gamma composed lambda prime t dt, and therefore I can write it as f of gamma t gamma prime t dt, provided you see, if I go back to the last lecture, not this one. Yeah, so here what was the statement? The statement was yeah, so here if I take integral over gamma 1 is same as integral over gamma 2. Here what is the condition? Gamma 1 and gamma 2 were integrals. So gamma 1 was from a to b, gamma 2 was from c to d, and lambda of c is equal to a, lambda of d is equal to b. So here the lambda, in our case lambda of a was becoming b, lambda of b was becoming a. So therefore accordingly one has to write down it carefully. So here, therefore here I have a, which is lambda of b, and this one b, which is lambda of a, or as I said, b is equal to lambda, yeah, b is equal to lambda of a and a equal to lambda of b. So if you replace this, I get a to b f of gamma t gamma prime t dt, and this is just usual real integral which is in the reverse direction. So I get this particular result. Okay, so therefore here also you see that if we go through the reverse path, I am going to get exactly a similar result that we have seen in case of real integral, exactly that kind of thing. Okay, so that's quite natural, and we have this statement. Now I want to have a more important statement coming up. So this one is about upper bound of complex integral. Okay, so I want to get upper bound of complex integral. So this is complex integral. Okay, so let us see what do I mean by this upper bound of complex integral. So again, we are going to recall what we have seen in case of real integral, and then we will try to uh, do that, and in our case, if we can, means whether we can extend that. So for example, in case of real integral, if I again go back to real integral, what do we have? I can, let's say, if I take an integral a to b ft dt in absolute value, we say that this is less than or equal to a to b mod of f t dt, right? Have you seen this inequality before?
Yes, sir.
Okay, so great. So I have this one. Now would like to, so this one gives you an upper bound for the this thing that you need for the integral that you need. Now this is exactly the same thing which I would like to have for my uh, function, for my integral, for my complex integral. So let us see if I can see something of this sort. So for example, let's say I want to have an upper bound for my integral over f. So do you think I can write this is less than over gamma mod of f? Do you think this will be, this will make sense? Can I do this? What do you think? In case of real, of course, that was the case. We just saw that this integral is less than this thing, where the integral is taken over the function mod of f. Okay, so can I write something like this over here? What do you think? Tell me.
No, sir.
Why?
Because f is u plus iv type, then the mod is u square plus v square ki power 1 upon 2. Then this is a real integration, and there is something.
So that is also, mod f is also real, right? Mod f
Yes.
is, yeah. So then, what? Why can't I write this?
सर here मतलब imaginary part और मतलब real part में से कोई एक unbounded हो सकता है. mod अगर bounded हुआ तो फिर
नहीं, mod बाउंडेड है तो रियल पार्ट इमेजिनरी पार्ट सारे बाउंडेड होंगे, क्योंकि we have seen, right, that mod of absolute value of real part of z comma absolute value of imaginary part of z is less than or equal to mod z, which is less than or equal to mod of real part of z plus mod of imaginary part of z.
Yes, sir.
So वो तो उसमें तो रियल इमेजिनरी पार्ट में कोई दिक्कत नहीं आएगा. mod f भी इट्स अ नॉन नेगेटिव फंक्शन. दिक्कत क्या है इस टाइम बेसिकली? Okay.
Gamma dash.
Sorry, come on, come again. कोई कुछ बोल रहा था, बोलो फिर से. हेलो.
गामा डैश कॉम्प्लेक्स नंबर हो जाएगा फिर डायरेक्ट, मतलब इक्वलिटी कैसे दिख.
Exactly, that is the point. So you see, what is this guy? If we try to write down, so this guy is integral over. So this guy is, let's say gamma is a path from a to b. So this is a to b mod of f of, or like maybe right, f of gamma t iska mod फिर gamma prime t dt. Now abhi gamma is a complex path, right? So whatever is this gamma prime, of course I can write it as real part plus imaginary part. So whatever is there, there's still some complex parameter is there. So it will have a imaginary part. So therefore, this number as a whole, this is a complex number a priori. Correct? Do you all agree to this from this expression? Yes.
Yes, sir.
Yes, sir.
It's a complex number a priori. So I can't write this because there is no inequality in complex number, and this is of course a non-negative real
So
number. Let me understand.
we can compare real complex number.
Sorry.
So we can compare complex number.
How?
That's what I was saying.
Yeah, we can't. Yeah, we are saying, that's what I'm saying, that we can't compare to complex numbers. So that is the reason why writing this whole thing is not quite correct. Is it clear to all of you? I can't write this. Yes? Do you agree
Yes.
to this?
Yes, sir.
Okay, so that's great. So we agreed to this. So let us now see what I can, instead of this, what can I do? So for that, it's important that I go back to the equation that I had in case of the inequality that I had in case of real integral. So you see here, what I said eventually means my aim is to get an upper bound. Okay. So let us say here I have this integral a to b mod of ft dt. This is what I need to means like this is my upper bound which I said. Now let us make it slightly more precise in the sense, suppose I take that my f is bounded above by some number which is capital M. Okay, so suppose my f is in absolute value is bounded above by some number, some real number m, then I will be able to write that this is less than or equal to m times b minus a, where mod of f is less than or equal to m for all t in closed interval ab. For all t in closed interval ab or open interval ab, whatever it is. Fine. So do you agree to this? If I have an upper bound for this thing, I will be able to, if I have an upper bound for the function mod f, then I will get this in more precise inequality, or like means I'm not saying more precise, but in the sense I don't have to do any integration. It's just mod f times b minus a. Will you agree to this?
Yes, sir.
Yes,
Okay. What we are going to do, we are going to do a similar thing over here. Okay, so here one thing that you should observe, that this, what is this b minus a? This b minus a is the length of the integral, right? Or length of the interval where I am integrating. So this is length of the interval Okay, great. So this is what is, let's keep that version in our mind, and with that we are going to prove the following theorem. Of course, the proof is one line essentially, but as I said, this is this particular information that I'm going to write down now is going to be very crucial. We are going to use it several times in our course, you will see. So this is called ML inequality. So this is called ML inequality. So what is ML inequality? So let gamma be a piecewise smooth curve. And f is defined, or f defined on trace of gamma and continuous, so that I can make sense of the integral. Then what do I have? Then I have m of then I have integral over gamma of f in absolute value is less than or equal to m gamma times L gamma. So what is m gamma and L gamma? Where m gamma is supremum t belongs to closed interval ab mod of f of gamma t. Okay, so that means supremum of f on the trace of gamma. And what is L gamma? L gamma is A to B mod of gamma prime t dt. So this guy is nothing but, if you remember, we had told in the beginning, this is nothing but length of gamma. Okay, so in the last class I had mentioned this. So what do I have? So we have this ML inequality, so which says that integral of f over gamma is less than or equal to m gamma times L gamma, where m gamma is the maximum of my function, like, or some upper bound or some supremum of my function on this, on the trace of gamma, and L gamma is the length of gamma. Okay, so I have this particular inequality. Again, as I said, the proof is going to be very easy, but you need to remember that we are not supposed to write anything what I wrote in the beginning. Like this one is a strict no, but we can get this particular bound. So integral of f over gamma is going to be less than or equal to m times L, or m gamma times L gamma, where m gamma is the supremum over all the functional values, and L gamma is going to be the length of the curve. So this is called ML inequality. Okay, so the correct way for us to remember, or like to remember this upper bound, or this particular inequality that we see in case of real integral, is in form of the last quantity. So you see here in the end I have m times b minus a. Okay, so the integral a to b ft dt in absolute value is less than or equal to m times b minus a, where m is some upper bound for mod of f, and b minus a is the length of the interval. Okay, so if I remember this inequality in this way, then I am going to get the complex inequality or complex variant in a it will always stay with you. You are not going to make mistakes like this, which I told you in the beginning. Okay, is it clear? Is the statement clear?
Yes, sir.
Okay, fine. So we have this, and therefore now I have to do this, prove this statement. Okay, so I have to start by saying that, okay, this was I was doing this thing, the real inequality, the real integral case, the first inequality. I could do it for real valued function and all that. So first I will need a variant of this for complex valued function, and then I am going to like, then the proof will be one line. So let us see, what do I want to do? Okay, proof. Okay, so proof. So I want to first prove the following thing, that if I have a complex valued function defined on some closed interval AB, then I can nevertheless write down a similar kind of inequality. So let us see, what do I mean by that. So for example, suppose, so let G from closed interval AB to C be continuous. Okay, then I want to prove that, or piecewise continuous, whatever it is. If piecewise continuous is also fine, piecewise continuous, then A to B in absolute value gt dt is less than or equal to A to B mod of gt dt. Okay, so this is what I have. I'm going to prove this one. So remember here, in case of real integral, the formula, the inequality that I had, this was correct, but here my functions were all real valued functions. So here I am saying that even for complex valued function, there is no problem. Okay, so I can do the same thing. So let us see, how am I going to do this. So this part is not very difficult. So write integral a to b gt dt. So this is going to make sense because my g is piecewise continuous and all that. So all this can be, so I can find out this integral. Even you can separate the real and imaginary part, and you can find the integral. And so let us call this guy is r e power I theta. So this is some complex number. If it is 0, of course, I have nothing to do. So it means therefore I will allow r to be bigger than or equal to 0. So for some r bigger than or equal to 0. So theta is whatever theta you wish. Okay, so this one, let us write it like this now. So therefore, what do I get? What is the absolute value? The absolute value in this case is going to be r, and therefore what I can do is that I can write this r, of course, from the above thing I can write this is as a to b gt e power minus I theta dt. Okay, because theta is anyway fixed, some fixed constant theta. Okay, so whatever value of theta you think, I'll just take it like this. Okay, fine. So r is a to b gt e power minus I theta dt. Fine. So here now I have to means consider this particular integral. So what I do is that I write, so we write gt into e power I theta minus I theta. I write it as real and imaginary part. So let us say at plus ibt. I write like this. So real and imaginary part, where a, b are real valued function. Real valued function. Okay, so I have this. So therefore, so what we get? So r is therefore I have a to b at plus ibt, or at plus ibt whole thing dt. So this is what is my r. Now remember, a and b, each of them are real valued function. So therefore what I essentially get, I get that, and so this implies r is equal to a to b at dt, because this imaginary part, that integral has to be 0. Okay, because r is already a real number for me. So therefore r equal to a to b at dt, and maybe there are too many a b's, but okay, so let me write a tilde b tilde, doesn't matter. Okay, so this is what I have now. What is a? A is the real part of gt e power minus I theta. So let us write down that. So this is a to b, real part of gt e power minus I theta dt. So this is what is my a. Okay, so here let us observe one thing. So first of all, here you will agree to that for any complex number, if I consider the real part of z, any complex number z, real part of z will be less than or equal to mod of real part of z, and which will be less than or equal to mod z. Okay, so therefore what I can say here, so you see now these are all real thing. So what I can say is that r, which is that particular integral a to b real part of gt e power minus I theta dt. So this guy is less than or equal to a to b mod of real part of gt e power I theta minus I theta whole thing dt, and the real part, as I said, is in absolute value is less than or equal to the mod. So mod gt e power minus I theta dt. Of course, e power minus I theta has absolute value 1, so a to b mod of gt dt. Okay, so what was r? R was the absolute value of this integral. Okay, so that is what was my r. So that is what I get, a to b in absolute value a to b gt dt is less than or equal to a to b mod of gt dt. So therefore what it seems, that whatever inequality I had written for real integral, so the same inequality is going to hold true if I have just a complex valued function, but this time defined over closed interval ab, not defined over trace of gamma. Okay, so there is slight difference over here. In this particular statement, whatever my f was, that was defined on trace of gamma, but in the lemma or whatever the initial step that I have done, here my g is defined over closed interval ab. Okay, so for that particular case I have written down this inequality. Okay, so do not write this inequality for any function. Okay, so you can, what we see effectively is that this particular inequality is true if your function is defined over closed interval AB or on some subsets of R where you are taking integral. But in case of my complex integration, you need to remember that my function is no longer defined on an interval. This we have already told in the last class. My functions are defined on the trace of a gamma on which I want to integrate my function. So therefore, I now can write down that integral of f over gamma in absolute value. So this guy is what? This is absolute value a to b f of gamma t gamma prime t dt in absolute value. And now I know that this whole thing, f was not defined on closed interval AB, but the whole thing f composed gamma of t times gamma prime t, this whole damn thing is defined on closed interval ABs or whatever in subsets of R. So therefore here I can say that this is a to b mod of f of gamma t times mod of gamma prime t dt. Okay, and once I have that, you know that m gamma was supremum of all of them, so I can write that this is less than or equal to m gamma times integral a to b mod of gamma prime t dt, and which is nothing but m gamma times l gamma. Okay, so this is what we have, that the integral means we get the ml inequality. Okay, so is the proof clear? Tell me.
Yes, sir.
Yes, sir.
Yeah, so here there were two steps. You see, immediately we means I could have written down this kind of a step immediately, but that would not have been justified, because just before all this prelude I said whatever the real integral, the inequality that we have in real integral, we are not supposed to write that blindly. But so we understood that in which case we could write down a similar inequality. So we understood that, for example, if my function g is defined on closed interval AB to C, complex valued function, then also I can do the same thing. I can do a similar thing over here, and this is slightly different than writing this. So writing this and writing this, these two are two different things that you need to keep in mind. Fine, so we did it for complex valued function, and once I did it over here, we can immediately apply that for the function f of gamma t gamma prime t. This is a function defined over closed interval AB and taking complex values. So we get that, we get our ML inequality. So this is going to be a very powerful statement. Okay, so we will see, for example, let me just make a corollary right away, so that these things when we use it will be really handy to have this statement. Okay, so suppose let fn be a sequence of continuous functions such that fn converges to f uniformly on trace of gamma. Okay, so I have a piecewise smooth gamma, and I have a sequence of continuous functions such that fn converges to f uniformly on the trace of gamma. Okay, so I have this. Then what I can say is that if I have this, then we will be able to say that integral of f over gamma is nothing but limit n tending to infinity integral of fn's over gamma. Okay, so what it says is that the integral and the limit are interchangeable. Okay, so when I have a sequence of uniformly convergent function, and then if I have to consider the integral of the limiting function, that is same as first considering the integral of each of the functions and then taking the limit. Okay, so how do I prove this? So the proof is not going to be very difficult. The proof is easy. So let epsilon greater than 0 be given. Okay, and once epsilon is given, what I can do is that, you see, since Fn, so often uniform convergence I write with 2 arrows. So since Fn converges to F uniformly on trace of gamma, so then what we can say, so there exists n naught in natural numbers such that exactly the same definition over here, norm of, or the absolute value, or let me write the supremum of t over closed interval ab, mod of f of, or fn of t minus f of t. This supremum is less than epsilon for all n bigger than or equal to n naught. Okay, so this is the definition of this is the definition of uniform convergence. So therefore, hence what I get, hence if I consider this difference of the integral, so in absolute value, what is integral of f minus integral of fn, this is which is nothing but in absolute value integral over gamma f minus fn. So this whole thing is less than epsilon times length of gamma. Okay, so this is my ML inequality, or yeah, if I want less than or equal to my ML inequality. Okay, so now of course my epsilon was arbitrary. Since epsilon is arbitrary, we get this quantity as n tends to infinity. So this is for all n bigger than or equal to n naught. So as n tends to infinity, what we understand that this difference must go to 0 as n tends to infinity. So therefore we get integral of f is limit n tends to infinity integral of fn. Okay, so this is what was the statement, and we get it as a corollary of ML inequality. Okay, so here you can see that the length of gamma, that's a fixed constant, so it doesn't matter if there is some constant multiplied with your epsilon. It's really, it really does not matter. Okay, so this is one very powerful corollary of ML inequality, which tells us that if I have uniform convergence, then I can interchange integral and limit. Okay, so this is going to be a very important statement, because in that case you will see that we will be able to means, for example, in case of power series or certain things, we have already said kind of uniform convergence. So in those kind of scenarios we will be able to use this integral. Okay, means this particular corollary. Fine, is this clear?
Yes, sir.
Yeah. Okay, great. So now what I want to do, I want to tell you about the complex variation, means variant of this thing called fundamental theorem of calculus. Okay, so you have seen a fundamental theorem of calculus in for the real integral. So this time we will also prove complex version of fundamental theorem of calculus. Fundamental theorem of calculus. Okay, so let us see what is that. So let me write it down carefully. Just a second. Do I need this? Okay. Yeah. Okay, fine. So like the way, for example, if you have a function which you want to integrate, and suppose there is a primitive of that function in case of real integral. So what you have seen in case of real, in case of real, for example, I have to integrate a to b ft dt, and suppose that there exists a function, there exists capital F, such that your capital F prime t is equal to f of t in this range for t in AB. Okay, then what can you say? Then you can effectively say, or let's say in some interval containing AB also. If okay, so somewhere, let's say some interval containing AB. Okay, so I have this kind of thing. Then what do I get? What is this integral becomes?
F prime
FB minus FA.
Capital F.
Yeah,
B minus FA.
so this is what is the version of fundamental theorem of calculus. So here also we are going to do the similar thing. So theorem, let U be some open subset, U subset C be open, and I have gamma from closed interval AB to U, and this is a piecewise smooth curve again, piecewise smooth curve, piecewise smooth curve. This is what I have, and I have a continuous function if f from U to C be a continuous function such that or such that has a primitive primitive. Okay, so primitive means there exists a holomorphic function, that is there exists a holomorphic function capital F from U to C such that your capital F prime is equal to F. Okay, so I have a primitive of little f. Then if I consider the integral of f over gamma, this is nothing but capital F of gamma b minus capital F of gamma I. Okay, so this is what is the fundamental theorem of calculus that we can prove in this case. Okay, so let us quickly prove this one. So the proof is going to be very easy, and we are effectively going to use this real version, whatever we have. So here what I am going to do, I am going to do that sigma of t. So define, I am going to define a new function, define sigma of t is f composed gamma, so that is capital F composed gamma. So let us call this one is a sigma of t. Then sigma prime of t is going to be by chain rule f prime of gamma t and gamma prime of t. So this is what I have, and f prime of gamma t is nothing but f of little f of gamma t, gamma prime of t. So what we see, so integral of f over gamma, this becomes a to b, which is f of gamma t, gamma prime t dt. This is equal to a to b sigma prime of t dt, and therefore sigma of b minus sigma of a, and sigma is nothing but f of gamma t. So this is f of gamma b minus f of gamma a. Okay, so of course here I assume that even if I have f to be a function defined on closed interval AB and takes complex value, then we can still apply the fundamental theorem of calculus. Okay, so that is means like that follows effectively from just by separating real part and imaginary part. Okay, so whatever I have written over here, so using that itself you will be able to do it. So here of course in the real version my function little f was defined on closed interval AB and was taking real values. But even if I have a function let's say some g, which is a function defined on closed interval AB and taking complex value, then also you will be able to write down an analog of the fundamental theorem of calculus, which I have used over here. But since I have already shown you this kind of trick once, this I believe you will be able to do it. Okay, so here remember I have used, at least in this last step, I have used, if I can highlight, so in this particular step here for this equality, I have used fundamental theorem of calculus for real functions of real variable, but this time the function is complex valued, so that one has to give little bit of argument, but this is what I'll leave it as an exercise. Okay, so is this clear? Yeah.
Yes, sir.
Okay. So this part, please try to complete that thing, which, for example, like the way I have showed for ML inequality, you saw that I had to prove a variant for functions defined on closed interval a b to c. So similarly, the fundamental theorem of calculus also one can prove it for if I take any function from here to here. There also you will be able to see that gt dt is equal to capital GB minus GA, where where your G is such that the G prime of T is little g. Okay, so if I have such a function, you can nevertheless do it by just separating real part and imaginary part. Fine, this is what I have, and now let us go to some interesting points once I have this thing. So we will see, for example, in the
Sir,
yes.
sir, doesn't this imply for any path we get same integration?
Sorry.
For any path we get same integration.
For any path we get same integration, means any path between a and b, you meant?
Yes, sir.
So first of all, my gamma b and gamma a could be different, right? I
Yes,
don't
sir.
know.
Okay, okay.
Yeah, that could be different. And another thing, you see here, I have made a very important assumption that I am having a primitive, right? So it is important whether I can have a primitive or not. Okay, so if I can have a primitive, where does that primitive exist? Whether the primitive, like I can have a primitive which works in the set where I am interested in and all that. So all these things will be important. Okay, fine. We will see, of course, to what extent all these things like give you similar integral or the same integral. All these things we are going to discuss, because that is going to be some really important concept, and we will see how this existence of primitive, and of course when I take two paths such that this gamma b equal gamma of b equal to, let's say, gamma prime of b, gamma of a equal to gamma prime of a, and all that. So we will see how one can do that. Okay, so that is important. So yeah, okay, so let's get going. So one thing which I want to, we will be especially interested about are the following types of paths. Okay, so let gamma, what is happening? Yeah, let gamma be a piecewise smooth curve. Okay, so this one can define in general for any curve or any path, but I am doing it for piecewise smooth because I'm going to effectively use it for piecewise smooth curve. So let gamma be a piecewise smooth curve. We say, or let's say, yeah, okay, defined on closed interval AB to C. We say gamma is a closed curve if gamma of B is equal to gamma of A. Okay, so if gamma of B is equal to gamma of A, then we can, for example, means then we will say that our path gamma is a closed curve. Okay, so here in the closed curve itself, I am putting this thing that my path is piecewise smooth curve. Okay, so that when I just write closed curve, I don't have to write each time piecewise smooth and all that. Okay, so many times I'm going to work with closed curves, okay, which are like which for where I want to use the definition of integral or the formula for integral, so I need piecewise smooth. So for those things, means like, so that I don't have to write too much, and taking this closed curve, the definition of closed curves I'm giving for piecewise smooth curves only. Okay, so in other case also you can say, okay, even if it is not piecewise smooth, if you just have a continuous function from closed interval a b to c, you will call that curve or the path to be closed if gamma b is equal to gamma a. But for our purpose, because we are going to integrate on curves, and you have seen that to have a relatively easier integration formula for integration, we need to work with piecewise smooth things. So that is the reason I am defining this closed curve business only for piecewise smooth curve. Okay, so once I have this thing, then as a corollary of our statement that we just gave here about this fundamental theorem of calculus, what I get that if f has a primitive and gamma is closed, what do I get? Tell me, what is integral of f over gamma?
Zero.
So this guy is equal to 0. Okay, so now here I would like to bring one thing to your attention, is that, so remark, so consider the function f of z is equal to 1 over z. Okay, can you tell me if there is a function which is a primitive of this function? Like, do I have
Log z.
We have seen that. Okay, good. So I can take f of z to be log z, and I will get f prime is equal to f. This I will get. But can you tell me, where do I get this? In which domain do I get this? Do I get this in all c minus 0, or do I get in certain special domain?
In certain special domain, I think.
Like we have to take the set of complex numbers. I have to remove one ray starting from the origin, and some line I need to remove, isn't it?
Yes, sir.
So if we have seen, no matter what branch of logarithm and whatever else we take, the derivative is always going to be 1 upon z. But that derivative is 1 upon z is, that is like the derivative exists and is equal to 1 upon z, not on whole c, not on c minus some finitely many points, but rather c minus 1 ray starting from origin. So in those kind of sets, so now if you recall integral over gamma t, so I do not remember what exactly I had given, but let me write e to the power 2 pi it. So integral of gamma 1 upon z over e to the power 2 pi it, this curve, what was the integral?
2 pi it.
This 2 pi I, not t. There was no 2 pi, but it
Yes,
was
sir, 2 pi I. 2 pi I.
2 pi I. So that was the integral. So here you can means a priori it might look like that I was integrating over circle. So it was a closed curve, number one. And I was integrating 1 upon z, for which you might think that log is a primitive for this. But then where am I not getting 0? Where am I getting 2 pi I? So what you need to keep it in mind is that, you see, this primitive, it exists, but it does not exist in an open set where I am taking the path. So my path is, whereas my path is a circle, but I know that log cannot be like this derivative. Log is not even differentiable or not even continuous on such a thing. So I have to, like, if at all I need to work with log, I have to remove one line. Definitely I have to remove one line. There is no way. I have to really remove one line, and then only I can think of this derivative and all that for the logarithm. So therefore, you see, it might appear that the function 1 upon z has a primitive which is log, but still when I am integrating over a closed curve, I am not getting 0. So that shows, even in that way, that you cannot really have log in a way. Of course, we have already seen that log does not even become continuous in whole of c minus 0, but this also shows that you can't really have this log to be differentiable in like, let's say, on every point of a circle. Okay, so therefore we are getting this 2 pi I. So this is not equal to 0. There is a subtlety in this. Okay, so in other cases it was becoming 0. For example, if you just take z power minus m or z power m, we had taken m not equal to minus 1. M not equal to minus 1, then we had integrated over 2 pi it, and we had got 0, right? Correct?
Yes, sir.
So
Yes, sir.
you see, if I take m not equal to 0, then in all these cases, whether m is positive, negative, doesn't matter. In all these cases, they have a primitive either on c or in c minus 0. Is it clear to all of you?
Yes, sir.
If m is not equal to 0, m is not equal to -1, then z power m has a primitive, no matter what m you take, positive, negative, I don't care. As long as it's not equal to -1, it has a primitive in c minus 0. Okay, so I can work with, like for example, I can apply my fundamental theorem of calculus for the open set u to be c minus 0. Okay, so I can apply for this particular set, and I'll get this integral to be equal to 0. Okay, so now in the light of this fundamental theorem of calculus, these two integrals that we had calculated should means give you some more insight into how this integration thing, complex integration thing works. Is it fine? Is all of you have understood what I have said?
Yes.
Yeah. Okay, so
Yes, sir.
that's very crucial, and we will see more of this, of course. Anyway, so now let me see, what do I want to say. Okay, yeah, so now once I have this one, I would like to prove something stronger. Okay, so here you see that if I have a function which is having a primitive, then if I take the integral over a closed curve, then what I am getting is that the integration is going to be equal to 0. Okay, so what we are going to do is we are going to start with holomorphic functions this time, and then we are going to see that suppose I have a holomorphic function, and then can I say a similar thing over there. Okay, so for this I need to for example take functions, means we need to show we need to start with holomorphic functions, and then we will be proving a similar kind of statement, so which are called closed curve theorems for holomorphic functions. So let me just give a heading, so closed curve theorem for holomorphic functions. Okay, so this is what I'm going to prove. Okay, and often what I'm going to work with, we were working with closed curves. Okay, so we might work with simple closed curves. Okay, so simple closed curve means we will, for instance, work with closed curves which are 1 1 except the at the endpoints. Okay, so often we will work with simple closed curves. So that means by definition we have taken them to be piecewise smooth, and these ones means, so suppose I have a, this means I have a curve from gamma AB to C, so this one is going to be piecewise smooth, is gamma is 1 1 or injective. Gamma is injective on closed A open B, and gamma of A equal to gamma of B. Okay, so simple closed curve means it's going to be injective, and except the endpoints, everywhere means at the endpoints it's equal, and everywhere else they are not equal. Okay, so it's going to be injective thing. So these are called simple closed curves, and we are going to primarily work with simple closed curves. Okay, fine. So I have this anyway. So I'm going to work with them, and one thing which I would like to mention here is that generally, if I'm not saying it explicitly, so when I work with closed curves, okay, so the closed curve needs to have, like I need to, for example, let's say I just have one curve. Let's say this is a circle, or let's say I have a triangle. Okay, so which is given by a closed curve. So generally, you see, this is the point which is both gamma a and equal to gamma b. Okay, or let's say this is the point which is both gamma a equal to gamma b. So just from the picture, it might not be clear that in which direction my path is, like in which direction the path was traced. Okay, so in which direction I got this path. So generally, if I'm not saying anything, then we will always assume that the path was taken in the anti-clockwise direction. Okay, so that's the orientation we are going to always take if I'm not saying anything. So for closed curves, like if it is not a closed curve, then you understand that it starts at A, it ends with B. So you know how it has been traced. But if I take a closed curve, then since the end point and the starting point are the same, you do not really understand how it has started. So generally, we will take direction of the path to be in the anti-clockwise direction. Okay, so that is always going to be the case. And in some cases, if you do not understand, if you're, let's say, if your curve is very complicated, how do you understand what is the anti-clockwise direction? So anti-clockwise direction means the area inscribed by this closed curve should always lie towards the left of the curve. Okay, so for example, here you can see that this portion, when you are on the curve, let's say somebody is standing on this path, then he will see this area which has been inscribed by this closed curve is lying towards his left, his or her left. So that's how also one can define. But anyway, in most of the cases we will have simple looking curves, so it's not going to be very difficult to understand what is the direction. Okay, so if nothing is said, you are going to take closed curves with anti-clockwise direction. Okay, so that's going to be standard. Okay, so for example, we were taking this path e to the power 2 pi I t going from uh, t in closed interval 0 1. So that path was like it started here and came back here. So that was the orientation. So we are going to take these kind of things, anti-clockwise direction. Okay, so with this prelude about a simple closed curve, I want to start with the following theorem. Okay, so this is a very important theorem which is called the rectangle theorem, or depending on the which book you are looking at, this is also called the triangle theorem. Okay, so depending on what is your object, you will call it rectangle theorem or the triangle theorem. The proof is absolutely the same, there is no difference. Okay, so what is the statement over here? The statement is as follows. So this particular thing I am going to you need to be slightly careful with this statement. Okay, so that means like you don't means like, okay, you might feel that these statements are contradictory. So let me write it down and then we will explain. So let f be holomorphic on a ball. Okay, so on a ball b ar, let's say little r, let's say. Okay, and capital R be a rectangle slash triangle, okay, in BAR. Let gamma be the boundary of this rectangle or triangle, whichever you want to take. Then integral of f over gamma is going to be equal to 0. Okay, so what I am saying over here is that I have a ball, let's say somewhere, I don't care, some ball somewhere, and around a point A, and I have a rectangle in that ball, some rectangle like this or some triangle. I do not know if I can draw triangle. No, I can't. Okay, so anyway, so let's say I have a triangle somewhere here inside the ball. Okay, so what it says is that I have a function which is holomorphic in this whole ball. Okay, then if I consider a rectangle or a triangle, then if you take the integral over here, then on this closed curve, the integral is going to be equal to 0. So that is what we are going to prove. And of course, at this moment, you need to be careful about two things. Number one, here I am not going to be able to apply the fundamental theorem of calculus directly, because I do not yet know that holomorphic functions can have primitive and all this. Okay, so that is not, we don't have that, so I cannot apply that directly. That's number one. And another thing that you need to keep it in mind is that you see here what I am saying, that my function f needs to be holomorphic on the whole ball. Okay, so for example, in this 1 upon z, this case does not apply. Okay, so because 1 upon z is not holomorphic, no matter what ball you take around 0, 1 upon z is 1 upon z is not going to be holomorphic. Okay, so therefore clearly in this case, that particular theorem, or like means if I take the function 1 upon z, it's not going to be applicable. Of course, here I was integrating over a circle. Okay, but later we will see we can in fact integrate over any closed curve. At this moment I am starting out with rectangles and triangles. Later we will see something else as well, but take this for granted, means like take my word that for example functions like 1 upon z or 1 upon z square and things like this particular theorem is not applicable. Okay, so as I said, I have started by saying that closed curve theorem for holomorphic functions. So in this particular segment, I am going to work with functions which are going to be holomorphic in the whole of the curve, like not only on the curve, but also in the area where which the curve inscribes, and like perhaps little bit outside also. Okay, so my function is going to be holomorphic, and then I'm going to apply this theorem. Okay, so in cases like 1 upon z or 1 upon z square, this particular theorem is not applicable unless I am taking some closed curve which does not like for example 0 does not belong to the interior of the area which is inscribed by the curve. Okay, so remember that this theorem is applicable only for holomorphic functions at this moment. Okay, it might so happen like 1 over z square, we have seen integral of 1 over z square over the circle is equal to 0. So it might happen that there are some functions which are not holomorphic. I'm not saying on the circle, but let's say it's not holomorphic in the range in the area which is inscribed by the closed curve, but still I might get the integral to be 0 just because there is a primitive. Okay, so we have seen here that if there was this corollary, right, that if it has a primitive, then no matter what closed curve I take, I will always get the integral to be 0. So in particular, if I take rectangle or triangle, I will also get it to be equal to 0. So it might so happen that the integral of a function can be equal to 0 without the function being holomorphic, not on the curve, but let's say on the domain which is inscribed by the curve. So one needs to be slightly careful, okay, while applying this. So anyway, the time that I have, I'm going to complete this proof of this particular theorem. So let's get going. Okay, so mostly probably I think I'll perhaps prefer at the end the triangle version, but we will see what I can do. Okay, so I'm going to I'll try to explain proof in both the cases. Okay, so let's see. So let's try to draw a rectangle and let's try to draw a triangle, and then I will explain what I am going to do. So let's say I have a rectangle and let's say I have a triangle as well. Okay, so these are rectangles and triangles in some open ball, inside some open ball, and I have to show that I have a function which is holomorphic, and I need to show that the integral of this function along this gamma. So in my case, the gamma is this one. Okay, so this is gamma, and here this is the orientation of gamma. So I have to prove that this integral of f over these gammas are going to be equal to 0. Okay, fine. So what do I do? So first of all, denote integral of f over gamma by I. Okay, so that's our notation, and I need to show that this I is equal to 0, or in other words, what I am going to show that this I can be made arbitrarily small. Okay, so we will see how to do that. Okay, so okay, great. So what I am going to do over here, let me just tell you briefly. I am going to subdivide this rectangle into 4 pieces. Okay, like this. And now what I am going to notice is that, you see, if I concentrate on the integral of f along the boundary of the subrectangles, then what happens is that this integral gets added and gives us the actual integral. Okay, so what I am saying over here, so if I break my rectangle into 4 subrectangles, of course I am going to take all of them are of same let's say side, like the side will be divided by 2, the means height will be divided by 2 and all of that. So what I am saying is that if I break, but irrespective of that, if I break my rectangle into 4 subrectangles like the way I have done, and if I consider the integral along the boundary of the subrectangles, then my first claim is that they add up to the integral along the boundary of the bigger rectangle. Do you agree to this? Tell me if you agree to that or not. Yeah, so what effectively I am saying, let us say this is R1, R2, R3, R4. Then what effectively I am saying is that integral of f over gamma is equal to sum for I from 1 to up to 4 integral of sorry, this is little f over gamma I, sorry, not fi, gamma I, where gamma I is the boundary of Ri. Tell me if you agree to this or not.
Yes, sir.
Why is it true?
Because जो बीच में जो बन रहे हैं उनकी डायरेक्शन अपोजिट है तो वो कैंसिल हो जाएंगे.
Very good.
That's why.
Exactly. So this is what where we can use this thing that we have seen. If we take the reverse path, then the integral means the outcome of the integral that we get comes out with a negative sign. So let's say if I am looking at the integral over R1 over the rectangle, the boundary of the rectangle R1, then this part, of course, so let me use another ink. So this part, of course, contributes to the original integral. But there is some internal part like this, and then there is another part which contributes to the original integral. But notice that this part, the contribution from the internal part, one of them, is getting cancelled by contribution of another integral coming from the boundary of R4. Similarly, the contribution along this particular line is getting cancelled by the contribution coming from another line, means integral along the same line but in the reverse direction when I consider the rectangle R2. Okay, so that's why I specifically drew all these directions here explicitly, so that you see whichever line means you take which are inside this bigger rectangle, all of them are getting cancelled because there are some for one rectangle it's in one direction, for the other rectangle it's in the other direction. So when I put everything together, I get some cancellation, and eventually I end up having this. Do you all agree to this now? Yeah.
Yes.
Yes, sir.
Okay, so let us now see if I can do the same thing for the triangle as well. So let's take probably I should try to delete these things, so that okay. So what I'm going to do here also, I am going to first identify what are the midpoints of the sides of the triangle, and then I'm going to join them. Okay, so let's say this is my midpoint, I join it with this, and let's say this is my midpoint, so I join over here. Okay, so again I'm getting 4 triangles, call them R1, R2, R4, R1, R2, R3, R4. Okay, so here what I am going to have, again the same thing, this one followed by this, followed by this. For R2, this one followed by this, followed by this. For R3, this one followed by this one, followed by this. And R4, this one followed by this one, followed by this one. Okay, so you see, in doing all this, what I have got is that again the internal integrals are all getting cancelled, and eventually I have got that the sum of the integrals along R1, R2, R3, R4 is same as the sum of the integral, or sorry, gamma 1, gamma 2, gamma 3, gamma 4 is same as the integral along the curve capital gamma. Okay, great. So once we have that, what I can see is that, you see, all these 4 integrals add up to this the main integral, right? So what I can say is that in absolute value, so we must have that there exists some gamma I. Okay, so there exists I 1 less than or equal to I less than or equal to 4, such that integral along, so when I take the absolute value of integral along gamma I, that must be bigger than or equal to mod of I divided by 4. Okay, so I must be having one rectangle where the integral is at least as big as mod of I divided by 4. Okay, because if that means, so I is this quantity, I is this integral. So if each of the 4 segments give you in absolute value something which is less than mod I divided by 4, then triangle inequality is going to tell you that absolute value on the right hand side is going to be strictly less than I, whereas the absolute value on the left hand side is equal to mod of I. So that means you will get a contradiction. So therefore you can say that I definitely have one rectangle where I can say that the absolute value of the integral means along the boundary of that rectangle or triangle is going to be at least mod of I divided by 4. Is it clear to all of you?
Yes, sir.
Yes, sir.
Okay, so now without loss of generality, we are going to say that I is equal to 1. So this I can say without loss of generality, we can take I equal to 1. Okay, so I equal to 1. Okay, so if I have this, then what I am going to do? I am going to do a similar thing again. Now starting with the rectangle R1, I am going to again subdivide it into 2 parts. Okay, somehow it's not working, but okay, you understand what I am trying to do. So I am going to subdivide my rectangles again into four sub rectangles, and then try to do the same thing. Okay, here also I can try to do the same thing. Okay, like this I will break my triangle into 4 sub triangles. So, and I am going to continue a similar process. But now what you need to realize is the following thing. First of all, so here I am dividing it in this way. But observe that if I take the length of the gamma i's, okay, so for example, length of gamma 1 is definitely how can I compare the length of the gamma 1? Tell me, with length of gamma. Yes,
1/4.
is it 1/4? It's half.
Sir.
Half. So length of gamma is half of length of gamma 1 is half of length of gamma. And also, like, if I think of the diameter in the sense the maximum possible distance also between 2 points in R1, or let's say, yeah, is equal to half of the maximum possible distance between 2 points in R. Okay, so here, by doing this, what I am going to do, I am going to construct a nested sequence of rectangles, or nested sequence of triangles. And since the length of, or the let's say, yeah, the length and the diameter of the, means the length of the rectangles are, or whatever you call it, the circumference of the rectangles are getting smaller and smaller, also the diameter is getting smaller and smaller. So what you would be able to say is that this is a nested sequence of closed sets, or rather compact sets. And therefore what you are going to have, that these sets are going to be like, when I take the intersection of all these rectangles. So for example, what I was telling, that I was when did I write? Okay, so here I was so I was subdividing my rectangle into 4 pieces, right? So again I am going to, let's take the top rectangle, and again I am going to break it into 4 parts. Similarly, I'll continue doing this, and so on and so forth. So what will happen is that I'm getting a nested sequence of compact sets, where the area is becoming smaller and smaller. The area is becoming like smaller by a factor, probably one quarter. Yeah, so, and also the diameter. Okay, so the maximum possible distance is also getting smaller and smaller. So if you keep all this in mind, then what you will be able to say, that when I take these successive rectangles or successive triangles, then intersection of those rectangles and triangles is going to give you a, what is going to give you a, tell me?
Non-empty set.
Yeah, it's going to be a non-empty set. Not only that, it's going to be unique point, isn't it? Okay, so
Yes.
you will get a unique point anyway. So now what I'm going to do, I am going to use the fact that, and then that very point, you see, I have holomorphicity. Okay, so I have taken that my function is holomorphic in whole ball, and of course I do not know which is going to be the point which I'm going to get in the intersection, which is a non-empty intersection. I do not know whether it might lie on the boundary, or it might lie somewhere in the inside. Because if you, for example, after taking, let's say you in case of triangle, let's say your triangle that you want to work with is R3. So then clearly you are going to have something, let's say, inside the boundary. So some point you will get in the intersection, which might be on the boundary, or it might be somewhere inside. And we have this information about holomorphicity, so we are going to use that. And using this, we are going to we are going to show that I is going to become equal to 0. Okay, so I don't have time to complete this proof today, which we will do it in the next class. Okay, so remember this idea, that we are going to construct means rectangles and triangles in a nested manner, so that I get a point in the intersection. Okay, so that is what is going to be crucial. And we are also going to use, of course, how the length of the gamma is decreasing, or length of the integrals are decreasing, and with all of that I'm going to use ML inequality, and we are going to see that the integral is going to be small, like is going to be smaller than any positive epsilon that we wish for using the holomorphicity. Okay, so here in this particular theorem, holomorphicity in the whole ball is going to be crucial, because as I said, I am going to take nested rectangles, subrectangles, and so on and so forth, but I do not know at the end when I take this all this intersection which point it's going to be. It could be any point here. Okay, so depending on that, because we cannot control that, so therefore I need holomorphicity in the whole ball which contains this rectangle or this triangle. Okay, so that's why I have mentioned that all these things, like for one like 1 upon z square or 1 upon z cube, or for example 1 upon z, these things are not applicable. Okay, so this particular result, it really needs holomorphicity not only on the curve but rather on the ball. Okay, that is important. And okay, we will see the proof in the next class, and then we will take it forward from there, and we will hopefully we will get characterization of something, some kind of properties about holomorphic function. And remember, our main goal is to reach to the fact that any holomorphic function can have a power series expansion. So let's see, I will probably not be able to do it in this week, but perhaps next week. Okay, so fine, I'll stop here. If there are any questions, you can ask me.